All right, one more type of limit that I want to talk about is limits at infinity. All right, this is something that we didn't talk about on graphs, although this is a thing that you can talk about on graphs. So let me just, here's an example. Something like this. Let's say I have a function that looks like that, where this is a horizontal asymptote. All right. If you have this kind of a situation, you say the limit as x approaches infinity, let's call this f of x, in this case equals 2. I'm asking you, so what that means is, it means f of x has a horizontal asymptote at y equals 2 as x increases. Right? Horizontal asymptote when the x is going this way, in the increasing direction. Okay, that's what it means to say limit as x goes to infinity. I'm trying to avoid discussing exactly what infinity is. Infinity is not a number. It is a thing you can talk about, but you don't really have to believe or not believe that infinity is a real thing to say this. F of x has a horizontal asymptote when y has a horizontal asymptote at y equals 2. All right? It's easy to identify on the picture what the limit as x goes to infinity is, or as x goes to minus infinity means that the asymptote is experienced when the x is going backwards. And also these limits can fail to exist. Like in this case here, the limit as x goes to infinity is 2, but the limit as x goes to negative infinity of f of x, in this case, does not exist. That's because as we go this way, there is no particular y value that this function approaches in a horizontal asymptote. All right? So this limit does not exist. That's because there's no horizontal tote on the left. Right? So when you're going to negative infinity, which is that way, there is no horizontal asymptote. All right, what about looking at equations? This is a more interesting thing. Looking at the picture is pretty easy. All right, consider this. What if I give you an equation and I ask you what is the limit as x goes to whatever? All right. In equations, how do you do this? Where you don't necessarily know what the picture looks like, so you can't just look for horizontal asymptotes, which is easy to do if you know what the picture is. What about if you don't? Here's two simple facts. Simple facts. The limit as x goes to infinity of 1 over x to the power n, say, where this, if this n is a positive number, so I'm talking about something like 1 over x squared or 1 over x cubed or whatever, right? This equals 0. If you don't believe me, you can try to draw a graph of one of those kinds of things, 1 over x squared or 1 over x to the 1 power even. You know, 1 over x looks like this, right? In fact, they all look like this, at least on this side. Some of them are always positive. Some of them have this side being negative. But it doesn't matter. In any case, every function like 1 over x to some power, as long as that's a positive number, it approaches 0 as a horizontal asymptote when you go out to the right. That's all I'm saying right here. And it's also true in the other direction. I said sometimes these things look like that. If the power is even here, it'll look like this. If the power is odd, then instead the thing will be on the bottom. But in either case, when the x goes this way, to negative infinity, the limit is also 0. So here's my second, simple fact here. Limit as x goes to minus infinity, 1 over x to the n, is also equal to 0. Okay, so this is for any n greater than 0. This exponent has to be positive because the negative exponent actually refers to a reciprocal. So if you see a negative exponent in the bottom, that actually means it's a positive exponent in the top, but I don't want to get into that. I'm not going to try to trip you up by doing stuff like that. All right? This is true for any n greater than 0. So you can do some tricks here with limits. How about this? Limit as x goes to infinity of 3 over x. How about this? 3 over x squared minus 2 over x plus 6. All right? Because of what I just said, this part here and this part here You kind of know what the limit has to be, right? The limit of anything that looks like 1 over x to some power is always 0. If you want to make this look like that, you can rewrite it like this. This is the same as the limit of 3 times 1 over x squared plus, or I should maybe say minus 2 times 1 over x plus 6, right? And then I already know that this part here, the limit equals 0, and also this part here, the limit equals 0. So you can do the limit, and you get 3 times 0 minus 2 times 0. That's because this part is 0. This part is also 0 when you do the limit. And then plus 6. So what's my answer? 0, 0, plus 6. So the answer is 6. All right? Let's try some more. All right, how about this guy? Limit as x goes to infinity, x squared plus 7 divided by x to the 5 minus x. Let's try that one. I'm going to do a similar trick, divide out everything, but I'm not going to divide by x in this case. I want to put every x everywhere into a denominator. The strategy that you should do when you're trying to do this is divide by the biggest power of x you see. So I'm going to divide by x to the 5th, all right? Let's try it out, just like before. Lim x goes to infinity. Okay, on top I get x squared over x to the 5 plus 7 over x to the 5 divided by x to the 5 over x to the 5 minus x over x to the 5. Okay, let's simplify a little bit. What do you get here? I'm not going to do the limit yet. X squared over x to the 5. Do you remember how to do one of those guys? Exponents in fractions like this, you subtract the exponents. All the x squareds are going to cancel here, and what you remain, what's left over on the bottom is x cubed, right? Here, I'm just going to leave it like that, 7 over x to the 5. Down here, this here is 1. This here is 1 over x to the 5, right? No, x to the 4, right? Because I got to cancel one of the x's, then there's 4 left over. Okay, what do you do when you take the limit here? Well, it's the same thing, right? Everything which has x's on the bottom becomes 0, and everything else just stays like it is. So when I do the limit, actually, I get 0 plus 0 divided by 1 minus 0. And what is that? 0 divided by 1? Is that anything? Yeah, that equals 0. You know, you're not allowed to divide by 0. You can't have 0 on the bottom, but you definitely can have 0 on the top. It's just 0. Okay, so this limit is 0. Let's try and be a little cute about this. Let's be a little smart about this. I think actually, think about what could you change here. What if I change this around a little bit? How is that going to affect the answer? For example, if this 7 was an 8 instead, does that matter? No, it doesn't, because just make that an 8 here, 8 here. But this is going to turn into 0 anyway, right? In fact, everything here is going to turn to 0 and give you 0 over 1. I think really the only thing that matters is when you do this thing, divide out by x to the 5, you didn't cancel out all the x's, right? There still remain x's on the bottom of everything on the top. If you think about it, what this means, there's a nice little rule for this, which is very simple to understand, but takes a while to write down. I'll write it down. All right, here's the sweet trick for doing these limits as x goes to infinity. So in a fraction like this, limit as x goes to infinity, f of x over g of x for polynomials, f and g, right? The thing on the top and the bottom have to be polynomials in order for this trick to work. But here's the trick. We just saw the first part of this trick is if g has a higher degree. Remember, the degree of a polynomial is just the highest exponent that happens, right? The one we just did had an x to the 5 on the bottom, but only an x squared on the top, right? That means that when you divide everything out, you're going to kill off everything on the top. Everything on the top is going to become 0 when you do the limit. So if g has a higher degree, then the limit is 0. All right? You can just say immediately, it will always work out this way. If the degree of the thing on the bottom is bigger than the one on the top, the limit is 0. All right? We're going to talk about two other scenarios, right? One would be if the f is bigger than the g, and the other would be if they are equal. So leave a little space here. We'll come back to this, but that's what's in our future. All right? Okay, let's try one where the degree of the thing on the top is bigger. How about limit as x goes to infinity of 8x squared minus 7 divided by x plus 4, right? On the top I have a degree 2, on the bottom I have a degree 1. What are you going to do? Well, we're going to do the same trick like we did before. Divide everything out by the highest power of x which you see, which is x squared. So I'm going to change this into 8x squared over x squared minus 7 over x squared divided by x over x squared plus 4 over x squared. And now what happens? You just look through here and try to simplify. Okay, so that's going to be 8, right? 8x squared over x squared is 8. Minus 7 over x squared, you might as well just leave that as is. You can't cancel x's. Here I get 1 over x. Here I get 4 over x squared. Nothing to be done with that. But what happens when you take the limit? Everywhere you see x in the denominator, those things are going to be 0. That will be here, here, and here. They're all going to be 0. You get 8 divided by 0. So you say limit does not exist. All right? Again, there's very little about this original thing here which is relevant in getting this answer. You could change this thing around. All those numbers, the 8, the 7, the 4, they are irrelevant. The only thing that mattered was that the degree on the top was bigger than the degree on the bottom. That's what ensures you that everything on the bottom is going to turn to 0, whereas something on the top will not turn to 0 at the end. All right, so we can fill in the second thing on our little sweet trick. So what we just saw was when you have a higher degree on top, so if f has a higher degree, this will end up killing everything on the bottom when you divide out by the highest degree. So you're going to get all zeros on the bottom, which means, but you will not get 0 on the top. You get some constant on the top and 0 on the bottom. So that means then the limit does not exist. All right? Great. Okay, one last scenario. That is when the top and the bottom have equal degrees. Let's try this. 3x to the 5 minus 7x squared divided by 4x to the 5 plus x. How about that? All right? They have equal, both have degree 5, okay? I'm going to do the same trick as always, which is you divide out by the highest power of x that you see. In this case, it would be x to the 5, so this is limit x goes to infinity of 3x to the 5. I'm dividing everything by x to the 5, right? So next one over x to the 5, 4x to the 5 over x to the 5, plus here x over x to the 5. All right? Cancel some guys out, simplify. Limit x goes to infinity. Okay, this is, they cancel fully and you just get 3, right? And here, minus 7 over x to the 3, I believe. Downstairs, here they cancel, you get 4. Here you get 1 over x to the 4, all right? Now we take the limit. Everything with x on the bottom becomes a 0. That would be this and this. These stay like they are, though, so the answer is 3 minus 0 divided by 4 plus 0. You get 3 over 4. All right. So when the degrees of the top and the bottom are equal, you actually get some answer which is not 0, and you don't say the limit does not exist. You get an ordinary looking number, usually going to be a fraction. Can you identify where this came from in the original formula? I think you can. The 3 and the 4 are the coefficients of the highest degree term up there. All right. So that's our third part of the trick. So the last case is if f and g have the same degree, then the limit is the ratio of coefficients. Sorry, I'm running out of room here. The ratio of the coefficients on the highest degree terms, all right? In any case, either of these three options, you can say the answer immediately. It's very easy once you know the trick here to say what the answer is right away. And you know, when you're doing this stuff in class, I don't expect you to work out a whole bunch of details. You just tell me the answer right away because you remember the trick. All right, I hope you agree with me about how awesome this trick is. I didn't write it down before, but the exact same rules work when it's x going to minus infinity. It doesn't matter if it's plus or minus infinity. Anyway, you can do any example like this more or less immediately. I'm just going to write a few here. All right, what are the answers? You don't have to think really about this at all. You can just look at the formulas and say the answers immediately. Here, the degree on the bottom is bigger, so the answer is 0. Here, the degree on the, what about the degrees here? I'm actually being a little tricky here. The degrees are equal. I didn't write them right on top of each other, but the degrees are equal here, so the answer is the ratio of the coefficients on the highest degree terms. That would be this and this. What's the coefficient here? It's 1. It's a sort of invisible 1. So the answer here is -7. All right. How about this one? Again, the degrees are equal here. They're both degree 7. So the ratio of those coefficients is 6/4. There you go. You know, once you know the trick, you can say the answer immediately. Pretty good, huh?